Okay, what we're going to be doing today is looking at section 2.3 on formal logic. So this is going to be a little bit of a departure from what we were doing in the first couple sections where we're kind of introducing things and introducing some new terms. Okay, and then in 2.3 we talked about fallacies, but we talked about them in a way that you would, maybe very casually talk to, your friend about, arguments or ideas. Okay, it didn't seem like a math class where things were really precise, right? We gave some names to some things, but what we want to do now is we want to look at arguments formally. Okay, so what that means is that we're going to be looking at the form of the argument. Okay, so its form or its structure, how is it put together? Okay, and a lot of different arguments have the exact same type of reasoning, but with different words substituted. Okay, so they are structured the same way, but maybe they have like a different context. Okay. To give you a good analogy, in algebra, instead of writing like 2 + 3 = 5, right? Oftentimes, to look at the structure of what we're working with, we take away the numbers and we put in variables instead. Okay, and we can look at how things are put together. Okay, and sometimes we can even abstract beyond that. But the idea is that what we want to do is look at something that's true for a broad set of ideas, not just one specific argument at one time. Okay, so we still have some definitions and some terminology that we need to put together to make this happen. But what we want to do is sort of introduce the building blocks for arguments. Again, we want to look at this formally, looking at the form of the argument as opposed to just looking at the specific words for one specific argument. All right, so let's see what that sort of looks like. The most basic building block in math is typically numbers, right? When we're talking about arithmetic, when we talk about algebra, what we're working with is numbers, and we're looking at how do we put numbers together in different ways. In logic, what we're working with as our most basic building block are statements. Okay. So these are the basic building block of arguments. Okay. All right. Knowing what a number is typically very easy to do. Although I have an interesting story about that. Throughout history in math, there have been lots of arguments over what a number is. So the earliest that I know of goes back, I think, 2,300 years to the ancient Greeks, and their idea of numbers related a lot to geometry. Okay? And so they really liked the idea of all numbers as being able to be written as fractions. Okay, and so some guy came along and he demonstrated that if you draw a right triangle where the legs are of equal length, then the hypotenuse has a length that cannot be written as a fraction. It's not possible, right? Okay, so that concept at the time challenged what they thought of as numbers. Okay, and that happened again with introducing zero. That happened with introducing negatives. That happened with introducing what we call imaginary numbers. They're called imaginary because some people didn't really like this concept being introduced as a number, so they gave that they assigned the term imaginary to them, and it just kind of stuck. Okay, but anyway, I'm sort of digressing here. But typically, if if I were to write something down and ask you, is that a number? Okay, you can answer yes or no to that pretty easily. A statement can be a little bit more subtle, right? And we'll look at why in a minute. But first, let's define it. So a statement is a sentence that can be either true or false. Okay, so a statement is true. Well, I don't know if we need to really define what true and false are, but right, if what really happens is, if that statement describes what really happens, it's true. And if it doesn't correspond to reality, it's false. Okay, so not every sentence is a statement. For example, if I look at a question, questions are not true or false. Okay? The answer to a question might be true or false, but the question itself is not true or false. Because a question can't be true or false, when I write a question as a sentence, that is not what we call in logic a statement. Okay, so when we say statement here, we're speaking very specifically. All right, imperatives. Okay, so when I tell you to do something, say I say turn to page 378, again, whether or not you do that, right, you could either choose to do that or choose not to. But if somebody just says turn to page 378, okay, that's not true or false. Okay? Your response to that, right, saying I turned to page 378, you might have done that or you might not have. Okay, but the statement, that sentence itself isn't true or false, so it's not a statement. Okay. Similarly with exclamations. Right. If I say, "Oh no," okay, there's no true or falseness to that. Okay, it's not describing what's going on. It's just my reaction to things. Okay. There are also some sentences that look like statements but don't really make sense. Okay, so if we just say something like that's just nonsense or gibberish, okay, then that's not a statement. Okay, so for example, if we say the number 7 melts at 35 degrees Celsius, okay, I don't know what that means. What does a number melting even mean? I don't know what that sentence is saying, okay? And if this doesn't really have any meaning, right, if melting isn't something that a number can do, then saying that a number is melting doesn't have any meaning, right? Okay. Okay. Numbers don't melt, so the sentence isn't saying anything, so that's not a statement, right? It's not true or false. Okay. There's another type of sentence that really looks like a logic sentence but creates a lot of problems in logic. Okay. This is called a paradox. Okay. And here's a great example of that. This sentence is false. Okay. If you try to assign a truth value to that sentence, you'll always fail. If I tell you that this sentence is true, the sentence itself says that it's false. So that doesn't really make sense. If I say that this sentence is true, but the sentence that I'm saying is true is that it's false, I'm clearly wrong. Okay? So then the sentence must be false. But the sentence says that it's false. So if the sentence is false, then it is correct, which means the sentence is true, but it says that it's false. And again, you can see how this is kind of running into a crazy cycle, and you can't make sense of it, right? So if we say the sentence is true, okay, then the sentence itself says that it's false, So if we say the sentence is true, the sentence is false is true. Okay, so we were wrong. Okay, if we say the sentence is false, I should make this a little bigger. Okay, if we say the sentence is false, okay, then the sentence is false is true. Wait a minute. Sorry, if we say the sentence is true, my first line, then the sentence is false. See how easy it is to get mixed up with these. All right, if we say the sentence is true, then the sentence itself, the sentence is false, right? Is false. Okay, so we are wrong. If we say the sentence is false, then the statement the sentence is false is true. Okay, so that when we said that it was false, we are wrong. So no matter how we try to assign a truth value to the sentence, whether we say it's true or we say it's false, we're always wrong, which means there's no other option. We can't assign a truth value to it. So even though it looks like it should be a statement, it is not, because it can't be assigned a truth value. Okay. We don't want to spend a lot of time talking about paradoxes. We could spend a whole class on it, but there's a lot of confusion that can go on there, and that's not the direction that we really want to spend our efforts. Okay. Oftentimes, sorry. So we are wrong. Yeah. So either way we assign a truth value, we're always wrong. Okay. And this often happens with a sentence that refers back to itself. Okay. And there's lots of examples of these. You could probably get a whole book on things like this, right? And the problems that they cause. Not all paradoxes have to refer to themselves, but those are good examples of things that are not a statement. Okay, so when we say statement, we're immediately eliminating things that create these paradoxes. Okay, there are other sentences that might be poorly defined, okay, where we can't really tell if they're true or false because it's hard to say what they mean. Okay, so there we go. So we can't tell if they're true or false. Okay, and let me give you some examples. This first one is Yellow Submarine is the best Beatles album. Okay. The trouble there is, I might say that Yellow Submarine is, and somebody else might say that it's not. And what we're expressing is opinions. So if I just say that it's the best, right, like that's not really clear, like what makes it the best. Okay. So in this case, it's not clear what the best is. Okay. Okay, so if we don't have like a very precise definition of what best is, then we can't say that, right? And the problem originates from the sentence is really just an opinion. Okay, there's nothing wrong with opinions, but opinions aren't really a good statement because it doesn't have a clear true or false value. Okay, because for different people, that might be different, right? All right, so the way that we can change this a little bit to make it a statement is by being more clear about what we're talking about by defining the terms. For example, if we say Yellow Submarine is Alice's favorite Beatles album, okay, then this is either true or false about Alice, right? Okay. Now, whether or not you know whether, about Alice and her love of this Yellow Submarine isn't important. You don't have to know the truth value of a statement for it to be a statement. Okay. For example, if I say it's raining in London, right? Unless you've looked at the weather report recently in Europe, you don't know whether or not that's true or false. But it is either true or false. Saying it's raining in London right now is something that could be verified, right? And either corresponds to reality or it doesn't. Okay. So we don't have to know whether or not something's true or false to know that something's a statement. Okay. So I know that, the sentence, it's raining in London, is a statement, even though I don't know if it's true or false. Okay. So when we talk about The Yellow Submarine is Alice's favorite Beatles album, okay, that is either true or false. And I don't know which one it is, but that's okay. All right. So if this is how I define best, right? If I say best is, whichever one is Alice's favorite Beatle album, or if I say best is whichever album is my favorite album, okay, then that becomes a statement. If I say, okay, Yellow Submarine sold more copies than any other Beatles album, okay, then we could go and we could verify this, right? Okay, we can look at album sales numbers to decide if this is true or false. Okay, so saying The Yellow Submarine is the best Beatles album is not a statement. But saying that Yellow Submarine is Alice's favorite Beatles album is a statement. And saying Yellow Submarine sold more copies than any other Beatles album is also a statement. Okay. So this is why, we said statements can be a little trickier than, say, numbers, right? When I write down 3, that's a number, right? Okay. If I write down yellow, that's not a number. Okay. In logic, statements can be a little bit more tricky. So maybe as a side note, when we study logic, we want to be at least a little bit forgiving so that, we have something to work with. So we might have some ambiguous statements like John is tall, okay? And tall is not really clearly defined, right? At least right in front of us, okay? So, a sentence like that can be a little bit tricky. But if we say, well, if there's some idea, if this seems like something that's probably clearly defined somewhere, okay, then we can say, all right, that we'll let that be a statement, right? So we have to be a little bit forgiving, otherwise we wouldn't really get anywhere with language because language has a lot of assumptions around it, right? Okay. So you should be able to say John is tall and uh, people should know what you mean. Okay, and I realize that that's an opinion, right? And we have to be careful, right? So we said earlier some of these were not a statement because they're an opinion. Okay, but if tall has like a specific meaning, like if tall means okay more than say 5 feet 10 inches, okay, then it's not an opinion anymore. So when we say that it's clearly defined somewhere, what we mean is that this can be a little bit more precise than just an opinion. All right. So there's a little bit of a gray area between, what are statements or not, depending on opinions. Okay. All right. So let's move on and look at what we can do with statements. All right, we said a statement can be either true or false. So let's first look at some examples of true statements. 2 plus 2 equals 4. That's a true statement. Anchorage, Alaska is further north than Springfield, Illinois. It's a true statement. If it is raining outside, then there is water falling out of the sky. Okay. This one is also a true statement, but this one is a little bit more complicated than the previous two, right? So here I have a sentence that's just written in math symbols. Okay. Here I have a sentence written in words, but both of these are sort of just like a straightforward sentence that just describes something. This third one tells me something based on something else, right? If it is raining outside, then there is water falling out of the sky. Okay, so this is a conditional sentence. Okay, it doesn't tell me whether or not water is falling out of the sky. It's sort of saying if it's raining outside, then there's water falling out of the sky. So it's sort of telling me, okay, when you have this condition, then this other thing happens. All right, those are true statements. Let's look at some false statements. 2 plus 3 equals 4 is a statement. It happens to be false. Okay. San Antonio, Texas is further north than Portland, Oregon. Again, that is a statement. It just happens to be false. All right. If it is raining outside, then it is also at least 70 degrees Fahrenheit. This last one is also a false statement because it's possible that it's raining outside and it is not at least 70 degrees Fahrenheit. You could have a cold rain, right? So all three of these are false. And this last one, again, is a little bit tricky. Okay. For a statement to be true, it needs to always be true. Right? So sometimes when it rains, it's at least 70 degrees Fahrenheit, and sometimes when it rains, it's not. Okay? So when we say the statement, if it is raining outside, then it is also at least 70 degrees Fahrenheit, our claim is about any time it's raining. Okay? And because that's not always true, we say that it's a false statement. Okay. All right. As we mentioned earlier, there's some statements that are either true or false. Okay. But we don't know which one. So for example, 2 plus x equals 4 is true if x is true. Okay. But it's false if x is a different number. Okay. It's also false if x is not a number at all. All right. You are further north than Rome, Italy. Okay. Now, at this moment, when I say this to you, you might know if that whether or not this is true or false. Okay. But if I read this to you tomorrow and you've taken a plane flight somewhere, then that might have changed. So whether or not this is true or false depends on where you are when you read this. Okay. Okay. So this statement can be true one day and false the next. Okay. It's still a statement, right? When I read this, you could verify whether it's true or false. Okay. But it may change. So it's not always true and it's not always false. It sort of depends on who is reading it and where they're sitting when they do. Okay. It will rain on April 29th, 2057 in Madrid, Spain. Okay. Again, this statement is either true or false, but we have no way of telling whether or not it's true or false. Okay. We won't know, for many years what's going on here, right? Was that 38-ish years? Okay. So this is either true or false. Okay. But we have no way of knowing right now. Uh, that's not 38. 36 years. Okay, and some months. Okay, so these are all statements. We just don't know whether or not they're true or false. Okay, they still get to be statements. All right, now we alluded to this a little bit earlier. Let's go into this in a little bit more detail. Okay, simple and compound statements. And once again, I think that it will be helpful if we use an analogy. So we're going to talk about algebra for a second. Okay. In algebra, we have these simple expressions. I can have a number on its own, like 5 or 2, or I can have a variable on its own, like x or y. And those are a simple expression, right? There's just one thing there. Okay, then we could have a more complicated expression that might involve numbers and variables. Okay, and here I have numbers and variables multiplied. Here I have numbers and variables, and I have multiplication and addition, right, or multiplication and subtraction. Okay, so it's more complicated. I have combined some of my simple expressions together to get a more complicated expression. Okay, now when I look at this, 5xy squared is still an expression. Okay, it has expressions as some of its component pieces, but when I put it all together, it's still an expression. Okay, so this is a good analogy because we do the same thing with statements. We can take a compound statement, which is just a statement, okay, but it's comprised of a bunch of pieces, right, like the 5xy squared. Okay, so a compound statement is a statement with smaller meaningful parts that are by themselves statements. And a simple statement is a statement that can't be broken down that way. Okay, so let's look at an example, right? So like with algebra, if I talk about 5, you can't break that down into smaller pieces. There's just a 5 there, okay? But 5xy squared, I could say, well, I have a 5, I have an x, I have a y squared, okay? The 5 and the x and the y squared are all smaller pieces, okay? The y squared could be broken down further into a y times y, okay? But just a 5 by itself can't be broken down. Okay, let's look at what this looks like with sentences. if it rains on Saturday, then I do the laundry on Saturday. Okay. Then this statement has two simpler pieces. Okay. It rains on Saturday is one simpler part. Okay. And I do the laundry on Sunday is another simple part. Okay. So it rains on Saturday. There's no way to break that down further. Okay. So when we say it rains on Saturday, that's a simple statement. I do the laundry on Sunday, that's a simple statement. These are simple statements. Okay. They're combined together to make our original statement, which we're going to call a compound statement. Okay. So the compound statement also expresses a relationship between these two. Okay. Now, we have to be careful when we talk about a compound statement. We want to be careful that it really is a compound statement. Okay, so let's give you some examples. This is a compound statement. Alice has a cat and a dog. The simple statements that comprise it are Alice has a cat, and the second statement is Alice has a dog. And I realize I wrote those in opposite order, right? I wrote the sentence, Alice has a dog and a cat. Okay, but these are still both simple statements that are combined together to give me Alice has a dog and a cat. All right. This next one looks structurally very similar, but it is not a compound statement. This says Alice and Bob had a baby. Right? Well, this isn't the same thing if we break it down, right? If I try to break this down and say Alice had a baby, and then I write Bob had a baby, okay? The original sentence is different than these two sentences combined. If I say Alice had a baby, and then I also say Bob had a baby, okay, sometimes that might mean the same thing as saying Alice and Bob had a baby, but sometimes it may not. For example, Alice and Bob may not know each other, and if I say Alice had a baby and I say Bob had a baby, okay, those might not be the same baby, right? Maybe they're not together. But the original statement, Alice and Bob had a baby, is sort of connecting them together, okay? So that has this extra meaning. Alice and Bob have the same baby, okay? They're the baby's parents. So when we write Alice and Bob had a baby, there's more information than just Alice had a baby and Bob had a baby separately, right? It sort of built into our language is that they are connected, right? That they had the same baby, they're the baby's parents, okay? And we don't get that information when we break it up, okay? So that's why this is not a compound statement. There's more information there, okay? When I talk about the dog and the cat, we don't have that same connection. Alice has a cat, period. Alice has a dog, period. That's the same information as saying Alice has a dog and a cat. Okay, so that's why that's a compound statement. All right. What we're going to do now is we're going to start. Remember, we said that we wanted to do something called formal logic, where we look at the form of arguments. When we start talking about sentences, right, when we talk about like Alice and Bob and their baby, okay, it's very easy to get lost in the context, right? You start thinking about Alice and Bob together and their baby, right? Is the baby cute, right? Are they happy? Maybe they're tired. You're thinking about the context, and that sort of distracts you away from the structure of the sentence, okay? So what we want to do is see if we can formalize it and sort of take away the context for a minute if we want to just look at the form of the sentence. Okay. So in algebra, we do this. We often use letters, okay, which we call variables, right, to stand in for numbers. Okay, so instead of writing a number, right, I might write a variable instead, and that sort of generalizes it. Okay. In logic, we can use letters to stand for simple statements. Okay, so let me show you an example. Let's consider this statement: James and Katie did their homework. Okay, so this is a statement. It's a compound statement. I can break it down into two simpler pieces. So let's do that, right? So the two simpler pieces are that James did his homework. Okay. The second one is that Kate did her homework. Okay. And what we can do is we can use a single letter to take the place of each of these separate statements, right? So for this first one, we can do is we can say, okay, P is the statement James did his homework, and Q is the statement Kate did her homework. So then my original compound statement, this statement here, James and Kate did their homework, okay, I can write as the statement P and Q. Okay, and that way I can see the connection between them, and I'm not distracted by the context. Okay, it's also a lot shorter to write. All right, for statements, I wrote these as capitals. Okay, but for statements, we typically use lowercase letters. Okay, and we typically use letters from like the middle of the alphabet. Okay, so like P, Q, R, S, right? Those type of things. All right. Just like in algebra, I can have any letter be a variable. But if it's like an unknown quantity, I typically, like a variable quantity, we typically use things like X and Y and Z, right, when we're writing our equations. If somebody uses something like A, B, or C, that might be like an unknown constant, right? It has sort of a different context to it. And so we have these conventions that help keep things a little bit more clear. Okay. All right. So maybe I'll go back and I'll change my P and my Q to lowercase. Say, all right, we'll follow the convention and use a lowercase p. Oh, my P still looks capital. A lowercase p and a lowercase q to represent our statements here. All right. If I'm writing a math equation, and you write 2x plus y equals 2x plus 3, and that's the equation of a line, Okay. And I say, I don't want to write y equals 2x plus 3. I want to write capital A equals 2 smiley face plus 3. Okay. Is that the equation of a line? Sure, it is. My variables are just less clear. Okay. So it's not that this is wrong, it's just more confusing than it has to be. So if you're doing, if you're doing logic and you don't use lowercase, you use capitals instead, it's not that that's wrong, right? If you use A, B, and C instead of P and Q, again, you're not wrong, but maybe you're less clear than you could be because you're not using the same convention as everyone else. Okay, so this is also an equation of a line. It's just more confusing. Okay. When we write a variable like x or y, that might have a value, right? It might be equal to some number. When we talk about statements, they're going to be either true or false. So we say that a statement has a truth value. Okay. So let's talk about truth values really quickly. All right. The truth value of a statement is true, right? If, again, the statement is true, right? If it represents reality. We say it's false, or we might just write a capital F if the statement is false. Okay. So when we're, again, working with logic, it might be a lot easier just to write the T or the F to represent the truth value of a statement. Okay. That's a good reason why we might not ever want to use either T or F to represent the statement, because that would be really confusing, right? If I say that, it's very warm outside, and I write that statement as T, and you say, wait a minute, isn't that false? I'm like, well, no, T isn't the truth value. T is the name of the statement. Okay, now we're all confused. Okay, so don't use T or F as your letter that we use for the statement. Also, when we write T and F, we typically use uppercase so that we sort of have a couple layers of protection here against confusion. Okay, so there's only two possible truth values that a statement can have, right? Remember, a statement is either true or false. That's just two things. Okay, so there's only two possible truth values. So we can represent all of our truth values for our statement in something called a truth table. So what I'm going to do is start with one statement by itself. So here's an example of a truth table for one statement, P, okay, showing the two possible truth values. So here's P, and here are all the possibilities, right? It could either be true or it could be false. That's all the possibilities, right? All right, if I have two statements, suppose I have the statement P, I also have the statement Q, then there's four possible combinations of truth values. Okay, remember, each one can either only be true or false. However, I might have the situation where P is true and Q is true. I might have the situation where P is true and Q is false. I might have the situation where P is false, Q is true, or I might have the situation where both are false. Okay, so each one of these rows represents a possibility. Okay, so that's why it's all right to have T in here twice for P, because I'm not just looking at one by itself. I'm looking at the whole row as being like a possible reality, right? So I could have them both true, or the first one's true and the second's false. the first one's false and the second one's true, or they're both false. Okay, so if I have one statement, there's two possible values. If I have two statements, then when P is true, I have two possible truth values, and when P is false, I have two possible truth values. Okay, so when I add a second statement in, my number of possibilities doubles. If I were to add a third statement in, I could have all of these possible truth values when that third statement is true, and I could have all of these possible truth values when the third statement is false. So every time we add in a variable, we'll double the number of possible combinations. Okay. Right. So the number of combinations doubles each time we add in a new statement. Okay. So if I have one of them, there's going to be two possible truth values. If there's two, there will be four. If there's three, there will be eight. So if I want to write sort of a general formula for this, if I have n statements, there are 2 to the n possible combinations of truth values. Okay. So for 3 statements, there's 8 combinations. Okay. For 4 statements, right, there would be 16 combinations, and so on. Okay, that makes for a very big truth table, right? Once you start adding in enough statements, this can get, you know, large and complicated and messy. Okay, and that's not what we want to, you know, work with here. So we want to be aware that this can happen. Okay, but you know, we just want to be aware ahead of time when we do examples. I want you to see, okay, this is why we're not going to work with a lot of separate simple statements. If I want to create a truth table and I want something like 4 simple statements, I'm going to have these 16 combinations. Okay. If I'm talking about a real complicated argument, and maybe that argument has like 20 different statements to it, okay, simple statements, and we say, all right, let's build a truth value for that, okay, then I'm going to end up with over 1 million rows, right, for each of my possibilities, and that's not going to be something that we can write down. Okay, so you know, I just want you to be aware that when we create our examples, they're often going to be very simple examples with not very many statements, because the truth table gets complicated fast. All right. I think that's where I want to leave this today. What we're going to do is we're going to split these notes, I think, into a couple days. And what we'll do tomorrow is we'll get started with this next thing where we talk about negations. Because negations can, you know, it takes a little while. We're definitely not going to be able to finish the notes today. So I think this is probably a good place to cut it off. And then we'll finish this section hopefully tomorrow. How would the homework format look for this section? Well, that's a good question. There's going to be a lot of different things that the homework can look like. For example, you could be asked, right, is this a statement or not? Okay, and so that's going to look like here, where you could have a statement and it's just, you know, yes or no. Okay. There's also going to be some stuff where we put together truth values, right, and truth tables. And we need to sort of finish the section before you can see all of what the homework will look like. We'll talk about negations, and then that will, you know, and then we're going to look at other ways to combine statements together. which will eventually allow us to start building truth tables, right? It'll look like this. Okay. So I'm going to post up the homework, but you're not going to be able to do all of the homework yet, okay, because we haven't finished this section. So I'll post it up today, but don't expect to be able to get through all of it based on what we did today. Tomorrow we'll finish the notes for this section, and then that should cover everything.